folks, we have a little bit left on hydrogen bonding to do, and then we finished everything to do with covalent. So for homework I had given you this graph and I wanted you to state and explain the trend, and I said to be able to do that you have to look at the intermolecular forces for each compound. So if we look at the red line, so they're all AB4 molecules, which means they are tetrahedral in shape. They all have 4 bond pairs, so it is going, and they have the same element around a central atom. If you look at the electronegativity values for these, you will see that for all of these 4 compounds in the red line, they are all going to be nonpolar bonds, and by rule 1, if you have nonpolar bonds, these then will become a nonpolar molecule. For water then, as our next one. So water, when you draw it, it has 2 sets of lone pairs, like so. When you look at it is V-shaped or bent. It has 2 lone pairs, 2 bond pairs. When you look at the electronegativity values, you will get little negatives and little positives. So this is a polar molecule straight away, and it's the lone pairs by rule 3, and it has got strongest hydrogen bonding and weaker van der Waals. I should have said over here that these guys in this red line here, all they have is weaker van der Waals. So water here is going to have both weaker van der Waals, and it is also going to have strongest hydrogen bonding as its intermolecular force. So this has strongest hydrogen bonding, and it also has the weaker or weakest van der Waals as its intermolecular force. When you look at these guys over here, they're similar in shape or identical in shape to water. They have no hydrogen bonding because there's no NOF present, so they are V-shaped or bent. They have 2 lone pairs, and we've said by rule 3 the fact that they have lone pairs makes them polar molecules. So these guys will ever so slightly, if you were to draw them, so looking at this, they will be so weakly polar due to the lone pairs, not due to the polarity of the bonds. So these guys up here will have dipole-dipole interaction and weaker van der Waals. The dipole and the weaker van der Waals. So up here, hydrogen bonding and van der Waals. This red line down here, these are all nonpolar, so all these have are weaker van der Waals, and these guys here, because of the lone pairs, will have dipole-dipole and weaker van der Waals. Okay, so it asked you to state and explain. So we've talked about the IMFs that are in methane to tin hydride, and looking at the red line as the molecular mass increases, so I'm reading across the X first, the boiling point increases, reading the Y. So this line is going up like so. So then how do we explain it? It comes down to what are the intermolecular forces that are present. So as our molar mass increases, there will be more weaker van der Waals to overcome, and your boiling point gets higher. So it's the fact that there is the weaker van der Waals, your boiling point is going to get higher as your molecular mass increases. So that's your explanation for the red line. So then the blue line is weird in that the trend is water has a really high boiling point, and then it decreases but starts to increase again. So as the molar mass increases, the boiling point decreases initially before increasing. So that's explaining the curve of the blue line, and then what's the explanation? So we know now that this is one set of, that there are 2 different sets of intermolecular forces involved. So water has weaker van der Waals and strongest hydrogen bonding, so you need to mention both, and hence that's why it has a very high boiling point, and then compared to the others, as you go down the group, the hydrides formed, they're getting bigger in molecular mass, so they'll have more weaker van der Waals, and the lone pairs makes the molecule polar, giving the stronger dipole-dipole interactions. And that's why the boiling point is increasing as you go from H2S to H2TE. So we're putting together a couple of things here now, and just have to see, can you do your best? So state is always describe the line, and explain then is what thing can you use to explain why the line is that shape. So hydrogen bonding, you've seen it in the video last week, it is very, very weird. So you will get higher than expected boiling points, which we've seen in this graph here, compared to the rest of the group 6 hydrides, and that is because of hydrogen bonding. And the rest of the hydrides show the normal trend of increasing molecular mass and increasing molecular mass, increasing boiling point. But the reason why the lines are different for this and this is because of these guys have the dipole-dipole interactions. It has what's called a high specific heat capacity, so what that means is it can absorb a lot of heat energy with only a small change in temperature, and that has applications in a branch of chemistry called thermochemistry. Ice is less dense than water, so we saw that in the video, and I'll show you a picture in a second to explain that again. So ice will always float on water. So this on this side here, this is just little water molecules in a liquid, so there are some gaps between them, but these guys, if they were animated, would all be moving around. So this is in a liquid, and as soon as ice, or you start to cool from 4 degrees, so less than 4 degrees, the hydrogen bonds start to become fixed and regular, and you now have these gaps between all of the water molecules, and these gaps make ice less dense. It's also one of the reasons, so usually liquids, when you cool them, they'll contract and they'll keep contracting, but because of hydrogen bonding you don't get that, and ice is the solid actually gets bigger, it takes up more space, and because it takes up more space, then that's one of the reasons why pipes burst, and it's all to do with the fact that hydrogen bonds are present, and the frozen water has a very, very regular structure. You don't see in something that doesn't have hydrogen bonding, there will be no gaps. Your molecules will all be touching, no gaps at all. Okay, so just explain that, but the large empty spaces means it's now less dense and it will float on in water. So we've said both lone pairs are involved in hydrogen bonds, so each water is capable of bonding to 2 other water molecules, and that will continue on through the ice. In terms of just an idea of the energy that's required to break certain things, so we've said covalent bonds are intramolecular forces. So if you have trying to break in a water molecule, so we do a little diagram up here, if you have a water molecule and you're trying to break the covalent bond, so the OH bond, you would need to input 464 kilojoules per mole of energy. To overcome the hydrogen bond, and we've said that is the strongest of the 3 intermolecular forces we looked at, you have to input between 10 and 40 kilojoules per mole, so it's 10-fold less roughly, whereas van der Waals, which is the weakest of the 3 IMFs, you would have to only put in 10 kilojoules per mole to disrupt it. So if you have hydrogen bonds present, it's going to have much higher boiling point and melting point than expected, and you have to input a lot more energy to change the state of it. So this is just a little summary for you, you may find it helpful. If you have a non-polar molecule, it will only have the weaker van der Waals. If you have NOF present, NH, OH or FH, then you will have the strongest hydrogen bonding and the weaker van der Waals. And lastly, if you are a polar molecule but there's no NOF present, then you will have the strong dipole-dipole interactions and you will have the weaker van der Waals. So we'll try one question together and we'll see how you get on. So we're going to look at two different molecules and how do they differ in boiling point, viscosity and water solubility. So here we have propane and ethanol. So they both have a very similar molecular mass, which means their weaker van der Waals will be the same, which is good. So, but that doesn't explain why they have differences in boiling point. So if we look at the intermolecular forces for our propane, we would do the maths, C take away H, you're going to get 0.4, implies it's a non-polar bond, which makes and it's the same thing, all I have are H's all the way around. So by rule 1, a non-polar bond makes a non-polar molecule. So the only intermolecular force that propane has is the weaker van der Waals. So we now have a look here. So in terms of my carbons, I now have something different over here. And in your head you should be recognizing there's an OH, so you should be saying NOF. It implies there's hydrogen bonding. And if you look at the difference in electronegativity, this would be the minus, this would be the plus, and even if you look at the difference between C and O, you have a positive carbon and a negative oxygen. So straight away I have something weird in my compound. Everything else here is the same, and these are all non-polar. So the fact here that this would be polar, but it's got the super strong extra strength of hydrogen bonding present. So of these two molecules, the ethanol will have weaker van der Waals, but it will also have strongest hydrogen bonding, and this molecule would have the higher boiling point, would probably be more viscous, and would also be soluble in water. Okay, because it's a polar molecule and water is also polar. Okay, so that brings us to the end. There are some questions now for you to try. I am on Zoom if you have any queries, and there are a couple of little quizzes, and happy St. Patrick's Day.